So today basically I will try to simplify what NMR is, what NMR spectroscopy does, and then finally taking small steps, understanding onto the basic principle of NMR and how we can manipulate these features so that we get information about the structure of the proteins or any complex molecules you want to understand or elucidate. Okay, so if I start again with the electromagnetic spectrum. So electromagnetic spectrum today I have represented in a little bit different format. The idea is, we all know electromagnetic spectrum, right? And in the electromagnetic spectrum, the word itself has two two different small words. One is electro, one is magnetic. So if we talk about the waves nature of light, okay, so in wave nature of light is also described as an electromagnetic spectrum. Yes, Dr. Priyadarshini, you are saying something?
Huh?
Hello?
But it's not coming out.
Should I continue, Dr. Priyadarshini? Should I continue? Because I can hear some, like someone is... Okay. Okay. So, coming back to the electromagnetic spectrum. So when I'm talking of electromagnetic spectrum, we will be taking into consideration basically the electrical part as well as the magnetic part, right? Now here, magnetic part is equally important, because that is how, because of this magnetic property, we are going to extrapolate this magnetic property inherently present in atoms, and how best we are going to do it so that it gives some information about the structure, right? So as we all know, this is the electromagnetic spectrum. As we increase the wavelength, the energy associated with it decreases. That is like we have all understood, and I have been telling you, I think repeatedly, quite a few number of times till now. So apart from the wavelength, we see different, like these wavelengths are onto different, like small segments of wavelengths are separated onto different and they have been named. So similarly to this one, we have seen how in X-ray crystallography the X-rays are used. Here we will be focusing more on the pattern and more on the pattern of the basically the interactions of electrical as well as magnetic waves to give us the informations. Okay, now if we see first we consider basically a small atom. So I would like to all of you to recapitulate your class 9-10 physics, where I think everyone would agree or everyone would recall that you have atom, and atom can be further broken down or to small units. Basically it will be nucleus, and then the electronic cloud which is revolving around the nucleus. Okay, so in nucleus again there are two types. So there is neutron as well as proton. Now neutrons are usually, we know, they are not charged, they are neutral, but protons are positively charged, and that is how the nucleus overall gets its positive charge. And revolving are different like electrons in different orbitals, and when these electrons they are negatively charged, the electronic cloud keeps on moving across the orbit, and based on that, what we have to still understand is what are the quantum numbers. So there are different quantum numbers: principal quantum number, secondary quantum number, right, and then finally to spin quantum number. So I'll be focusing on the spin quantum number. Okay, now if I say like I think this is needless to explain what is principal quantum number and angular momentum. Now, still to give a rough idea or give like a background about it. So anything which is moving constantly will have some spin associated with it. Okay. Now this spins, if you can think of the solar system, the sun is basically the nucleus. Just imagine the sun is the nucleus which is positively charged, which comprises of neutrons as well as protons, and electrons are basically the different planets which are revolving around the orbitals, right? So this orbital are fixed and the movement path is also fixed, but that is not the only movement. Similarly, like in our solar system where earth revolves across the sun, similarly the electrons also keeps revolving around the nucleus, but the electrons in itself will also rotate, it will also spin, and when there is a spin there will be a angular momentum involved to it, right? Now this is important because when you understand the spin is always at an angle, and this angle will vary from electrons to electrons. So we need to understand the dimension, the direction of this spin, and based on this, what is happening, the movement and the pattern of the electron, or basically the electron cloud density over a period of time during the movement across the or around the nucleus can be defined. Okay. So when I am talking about the spin of a single electron, as you can see here, this single electron, this is basically behaves like a revolving like a small planet, and when there is a movement, there is a spin, there is an angle along with it. So either the direction will be towards up, as you can see the up arrow, or it can be towards down. So just for the representation purpose, I have made it like look like up and down, but it is like both the directions. Either it can be in the upside directional or it can be towards the downside directional. Okay, and based on that, what we do is we give spin quantum number as plus or minus half, right? So either it can be plus half or it can be minus half. When I'm talking of plus half, they have plus half will be in the particular direction, minus half will be in the other direction. Okay, so protons and neutrons in a nucleus behave as if they are spinning. Yes, that is also true. We must also understand that when in the nucleus you have the protons and the neutrons, they also behave as if they are spinning. Yes, but we are more worried about the electronic cloud, because from the electronic cloud the movement and the manipulation based on external influence or stimulus can be measured, right? And that is where we will be looking forward when you're talking of a NMR principle, right? Now if I just diversify the word NMR, it is nuclear magnetic resonance. So we have basically three words. Nuclear, we all know the word nuclear has come because of the nucleus. So basically we are focusing on to a single atom, and then from that atom we will try to manipulate the spin of the electrons to get information in our interest. Okay, now the other part is magnetic. So when I'm talking of magnetic, what is happening, your nucleus is basically two charges are there. The atom basically will have two charges, the nucleus as positive charge, the electrons as negative charge. So when an atom, if you think of as a whole, what happens is, by virtue of these two charges together present and they are spinning in their own axis, they behave like dipoles. So what are dipoles? There are two poles basically, or two poles plus or minus poles, and these atoms will behave like a dipole. Now these dipoles, as by the name I'm telling you, it will have two poles and they will behave like the charges are distributed onto the two sides of the poles. So they will also try to move, or they will try to have a momentum and have a spin. Okay, apart from, so the entire atom will also have some momentum. Now these dipoles, suppose one atom when it comes near another atom, they will have dipole interaction, because one dipole when it comes to another dipole or in the vicinity of another atom, what will happen, they will have the charge interactions between them, and that resultant will be a dipole interaction. Okay, but before going to dipole interaction, what I'm trying to explain is, in a dipole, as you see in this image, so if you think as a dipole, so it will behave like a small magnet. So it will behave like a small magnet, and these magnets also, they have poles, right? So they have north pole, south pole, and these atoms in whole will also behave like a dipole, and dipole will also behave like small magnets, because they will have magnetic field, and which can be traced onto them like a bar magnet. When you position it and onto the bar magnet, you can draw the magnetic fields. Okay, the lines of magnetic fields can be drawn, and that is where the magnetic field or the nuclear magnetic word comes from. Okay, and the third is resonance. So resonance is again a typical physics word. We resonate with different people. So what is that we resonate? We resonate with frequencies. Okay, so we resonate with different materials. Not we means like suppose you have a tuning fork, and a tuning fork, and you bang this tuning fork, and it keeps resonating, it keeps vibrating. But what happens, there is another tuning fork which is also vibrating at the same frequency. When you place them nearby, they will interact and they will resonate at the same frequency, right? So a very common example, suppose you must have encountered in your day-to-day life, when you have a good boom box, you have a good speaker with a woofer effect and everything, you just play it in the full volume. You will notice after a certain increase in volume, your window panes or glass panes in the house or nearby, they start making some noise. So what is happening, your boom box is generating some frequency, and this frequencies is picked up by the window panes or the glass panes, whatever are there. They also try to resonate at the same frequency. Resultant frequency will be higher. So there you hear the window panes, they are vibrating. That sound you can hear. Okay, so that is what a basic resonance means. Okay, and how it is relevant to NMR, I'll come to it in a while. Okay, now if we say that there are an n number of atoms in this environment, they are widely present everywhere. So do all of this are of our interest? Can we exploit them to have or to get the structural information out of them by using an NMR? Then the question comes, why I said about the spin quantum number. So the spin quantum number is important, because if your spin quantum number is even, the meaning is when you have the plus half and minus half complete in a particular atom, then that particular atom will not be suitable for NMR studies. Meaning, when you have odd number of neutrons and protons in simple, your spin quantum number will also be odd. It will be either plus half, it will be either minus half, and this type of atoms will be of interest from NMR point of view. For example, if you have one proton, you see one proton, 13 carbon, so you have carbon C12, but C12 is again even, so that will not be suitable to generate or to get informations in NMR. C13 is an isotope, and C13 isotope is not very widely present, so we have to at times enrich your sample with C13 isotope and then get the information. Similarly, nitrogen, we have N14 and N15. N14 is again odd number, the spin quantum number will be odd, will be even, and that is why N14 will not be suitable for NMR. N15 on the other hand is odd, and that is why. And similarly for fluorine as well as for phosphorus. So you see all this are commonly used, and we say there is a term called probes. So probes basically, if I see the environmental abundance of proton is huge, it's almost like 99%. The environmental abundance of C12 is also huge, but unfortunately C12 we cannot encapsulate for our studies. So C13, which is a rare isotope of carbon, and we have to enrich that on the sample to get the information. So carbon, nitrogen, proton, phosphorus, these are different probes which are usually present in your system, because based on this we have to see, based on the probes which is there in your NMR machine, we will be trapping a particular type of like either protons or carbon or nitrogen or phosphorus for that matter, and then we'll get a information and we'll get a spectra. So as the last word is spectroscopy, so we will get the spectra in the form of like different waves, and then from that spectra we have to decipher information which is hidden. So we need to understand how this spectra looks like and what are the patterns this spectra is going to tell us. Okay, now so again coming back to the spin quantum number, because this is a very very important concept. Once you understand this, I think rest of the part of the NMR will be much easier to track. So if you see here, this is a magnetic field in blue color, and you have this hydrogen nucleus, right? And this circle is basically the angular momentum which you can see here, and it is precessing at this particular, so you can see the red circle, and at a particular what you say as a cone, it keeps on precessing. Now in environment they are all in random formation. So if I talk of all this proton, carbon, phosphorus, okay, they are all randomly moving, right? Now I give a small example. Suppose as a classroom which is filled with 30 students, and there is no teacher in that classroom. What happens usually? Everybody will do what? Everybody will do whatever they feel like. They will talk. Like I will talk to my best friend, somebody will eat tiffin, somebody will draw something. So everything in that, so all these 30 students in that classroom, they are all random. Correct? Now what happens is, the similar way, this spin or the plus half, minus half, and then the angular momentum of this small spinning atoms, they will also be random. So this electrons, this orientation, the movement, everything will be random. Although they are spinning, although they have plus half, minus half, everything is there, but they are all random. Now what happens is, suppose in that same classroom a teacher enters. The moment a teacher enters, what happens is, everybody, all the students, they are aware that teacher has entered. Now they want to greet the teacher. They will say good morning ma'am, good morning sir, or whatever, right? So it is a way of greeting. What is happening? The moment teacher enters, most of the students, I am not saying 100%, so out of 30, like almost like 20-25 students will pay attention to the teacher, will be directional to the teacher and greet the teacher, right? So apart from this 25, there are 5 students. They do not bother. They simply do not bother. So they will carry on with their work, or at times they may simply ignore. So this is the same thing which is also happening when I am talking of an NMR condition. What is happening? In a random situation, all these spins are moving in different directions. They are not aligned. The moment they are put in an external magnetic field, so all these differently oriented spins, when they are experiencing a uniform external magnetic field, what will happen? Either they will align with that magnetic field, or they will repel with that magnetic field. Meaning most of the atoms will, the dipole-dipole interactions will be aligning towards the external magnetic field, and there will be a handful which will align against the magnetic field. Okay, so similarly some students, they don't abide by, they feel like they are better, or they do not need to listen to teacher or whatever, and they'll say no, we will not listen to the teacher, we will do whatever we have been doing. So if you see here, this is the spinning proton, okay, and this spinning proton, when they are all random in a normal condition with no external magnetic field being experienced. Now the moment an external magnetic field B naught is experienced by all of this, what happens, you see here, most of them will align towards the direction of the external magnetic field. Now this, why I'm saying most of it, because most of the spinning protons, they will have lower energy, and if you have lower energy, you will always align with a higher external energy which they're influencing. Okay, and why some of them will not align? Because they have inherent higher energy in their orientation. So because of that higher energy orientation, they will repel and they will align opposite, just opposite to the external magnetic field's direction. Okay, so this is the first thing when we are talking of. So what does, I'll come to this one, but first of all, let's see what this machine looks like, because if you understand the machine properly, then we will understand why this external magnetic field is coming and why this question of alignment is coming at the beginning. So this is NMR machine. It is almost 7 to 10 feet tall, and it is resting on anti-vibration pillars. You can see here anti-vibration pillars. The sample is loaded from the top. The red one you can see here, it is loaded on the top and it goes inside the bore, and this is basically the bore. Now the bore comprises of different layers, and basically this is a electromagnet. So electromagnet is when electric current is applied, it turns into a magnet. Okay, so this magnet is the external magnetic field, that is the B naught, which the sample experiences once the sample is placed within the inside the bore. Okay, now sample is taken usually in a NMR tube which looks like this. You can see a small tube where you can add something like your 20 to 30 microliter to 100 microliter maximum. You can add the fluid or the sample in a liquid format, and this is in liquid format. Why? Because once it is in liquid format, the spin movement and everything will be much better compared to a solid format. So in solid, the movement restrictions intermolecular and intramolecular are very much limited, and that is why it is always in liquid format. And in the liquid format, what we do is we prepare it in different solvents, right? So these solvents are basically medium where the sample will get dissolved. At the same time, they will not interfere with the chemical composition of your compound or of your compound of interest which you are going to study. Rather, they will also not, they should not in a way interfere with the structural orientation or with the NMR signals also, right? So to take care of that, there are a lot of standards are there. Usually D2O is deuterium oxide that is being used, and D2O is a very popularly used solvent for NMR, where you have, like if I take water, so water, as I was telling, you have proton, right? In proton, is NMR sensitive. So you cannot use water as a solvent for your sample to dilute, right? So we use usually D2O. D2O doesn't interfere. It will not interfere with the signals. It will not have electronegativity or influence onto the other nearby atoms which we need to study, right? So why I was talking of electronegativity and what would be the spin interaction, I'll come in a while again, okay? But for the moment, what you understand is you put your sample and this is the holder. So this basically is a sample holder which will fix it, which will actually drop and get stopped here. Now this is the area where the sample will be somewhat till here, okay, or little less than that, and your sample will experience what? The sample is a random classroom, right? It has all randomly moving protons in different directions. There is no control. Once this sample is loaded or positioned inside this magnet, so this is a superconducting magnet. Now why superconducting magnet? Because electromagnet, these are coils. So when you pass an electron, what happens is there will be a lot of electromagnetism and magnetic effect will be there, but there will be a heat generation. The conductivity of this coil will be creating resistance. So what happens is you fill or you plunge this electromagnet in pool of helium, liquid helium and liquid nitrogen. So liquid helium, liquid nitrogen, basically it will be in the -196 degree, and that will take care of reducing the temperature, or not, rather allowing the temperature to increase as and when system is running. And resultantly what happens is your electromagnet becomes a superconducting magnet with minimal resistance at that low temperature, okay? So what happens when you're positioning or you're dropping the sample inside this sample, or the present in the NMR tube, it is basically, the tube is made of a quartz glass, and this glass again does not interact with the magnetic field or to the sample. That is why quartz glass is there. So your sample is somewhere in this region and it will experience a magnetic field, external magnetic field, by virtue of this electromagnet. And that is where, so this is basically the teacher. So once you turn on and put your sample inside, so this is the electromagnet and this magnetic field is the B0 magnetic field, and this is the teacher which enters the classroom. So when the teacher enters, when this magnetic field is experienced, most of the protons will align towards the direction. Now if you see this consider this as a big magnet, okay? I think all of you can see this diagram, and consider this is a big magnet with a pole. So it will also have a pole, right? North pole and south pole. And the magnetic fields, as you see in bar magnets, you can draw the magnetic field lines. Similarly, you can also draw the magnetic field lines. And based on that, we always know that this bar magnet or this electromagnet, what we have here, what would be the magnetic field lines, and how my sample, which is positioned inside this NMR electromagnet, how it is going, in which direction it is going to experience the external magnetic field, okay? Now this is the static condition where your teacher has entered, everybody or almost all of the not 100% but at least 95% of the protons, they are aligning. So this is the condition. Now in this condition we are not able to get any signal. This is aligning. Suppose in the same situation, in the same classroom, one of the students suddenly, he dropped, or he opened his tiffin box and dropped it. So one student at the corner, suddenly the class is going on, the teacher is there, most of the students are serious about the class, they are facing the student, and one or two people, they are not very serious, they are doing their own job, and the teacher is taking the class. In this condition, all of a sudden one student opens up a stainless steel tiffin box, and then he drops that tiffin box. So there will be a sound, right? And this abrupt sound will attract the attention of rest of the people, rest of the classmates and the teacher at the same time. So this is what I am going to say as a radio frequency. Now this radio frequency is actually given, so a pulse of radio frequency is applied onto this sample, and then based on the reaction, the signal is being acquired. Okay, now what is happening? One student opened the box and dropped the tiffin box. Everybody immediately turned, right? Everybody, the immediate reaction will be to turn towards the sound source and then see from where the sound has come. Now there will be few students who are very serious about their study. The moment they see, okay, this is a small tiffin box, they will again quickly come back to face their teacher. They'll quickly turn their face towards the teacher and then face the teacher, and then follow with the study. They are very good students. There will be another group of students who will be more interested onto seeing what was there in the tiffin box rather than what the teacher is saying. So they will take little longer time. They will first take their own sweet time to explore the tiffin box, the student, the entire scenario, and then the teacher will say, okay, come back, focus here. Then they will focus onto their teacher. There will be another few group of people or group of students who will be much more interested, and they will be so interested that they now don't bother to listen to their teacher. They will go to the place where this has happened and try to either help or take the situation and see the situation, what is going on, and then try to talk among themselves, and they will get distracted. So that is actually happening when we give external radio frequency pulse or radio frequency pulse stimulus. So what is happening? In this environment, most of them are aligned towards the magnetic field, some of them are not aligned towards the magnetic field. At that scenario, all of a sudden there is a radio frequency pulse which has been given onto the sample. By facing this radio frequency pulse, what will happen? The spin or the orientation of the magnetic quantum spin direction will change, will get disrupted, okay, will get disturbed, and once it gets disturbed, it will be not aligning to the external magnetic field. But depending on the proton type and depending on the environment of the proton, depending on the neighboring protons, depending on the electronegativity of the proton, the time it will take, or it will take different time for different protons to come back to the previously aligned position. And based on this coming back duration, we get spectra. Okay, and this spectra will tell you what is the electronic environment this particular proton is experiencing, what are the nearest neighbor protons from this particular proton of interest, what may be the structure of the particular proton and with the combination of other protons, and it will give you the basic idea. Okay, so this is actually what is happening in your NMR system. I made it like I tried to tell you like a story, because if I go more and more as I'll go ahead, there will be more terminologies, there will be more complexities. So try to keep yourself as simple as possible. Take it like an instrument, and this is like a big magnet. So this magnet, inside this magnet you have a small bore, or you can see this bore or a pipe. Through this the sample goes inside, and once the sample is positioned here, obviously it will experience an external magnetic field. Based on the experience or based on this external magnetic field, what will happen? Either it will align towards the magnetic field or it will align against the magnetic field. Now a radio frequency pulse is given, and this short pulse of radiation will cause resonance, and because of this resonance and the pattern of the resonance of the protons, we will get the NMR spectrum, and then we will understand what this spectrum pattern tells us in essential. Okay, so now you see here, this is a magnetic pole and you see the proton. So this is the external magnetic field, and either the blue one is aligning towards the magnetic field and the H1 is aligning against the magnetic field. And what is happening here, when you are having this, either you get everything in the one side, and then that is the best case scenario, but it usually doesn't happen. And then what happens is you give the radio frequency pulse, and from the radio frequency pulse, what happens, most of the protons which are at lower or at a lower ground state, they will get that external pulse, radio frequency pulse, and they will jump onto higher orbital, higher energy state. So from alpha to beta state they will jump, but again once they jump, it will not be a stable position, because we all know excited state are always unstable. So when it goes to an unstable excited state, what will happen, it will try to get rid of that energy which they have acquired, and in that process they will give that signal, and this is the signal which we capture, and this is basically the frequency which we are looking for to tap and then convert it into a spectra. Okay, so again, yes, I think this is a much insider story. You see this magnet, and this is an electromagnet, that is why this coil is given. So whenever you pass a current, this electromagnet works as a magnet. When there is no current, it doesn't. But actually in case of an NMR, it is always, the electricity is always there, the system never shuts down, and that is why because of the temperature, because of the conductive issue, if you multiple times turn on and turn off the system may quench, the magnet may quench, and eventually your system may turn down. Okay, so what happens is the NMR system is never turned off, the electricity keeps flowing. Now because of the special alloy niobium ductile coils, okay, titanium niobium coils, so there are many alloy coils are there, based on which these coils are wrapped around inside the spore, and these coils become superconducting coils, because at lower temperature they practically do not give any resistance. So when there is no resistance, there is no heat generated out of it, and then they become superconducting magnets. So these superconducting magnets are always kept in, as I said, in liquid helium and liquid nitrogen to maintain the temperature, and inside this you have basically the sample. Now just onto the sample, or the wrapping the sample holder, you have another two coils which are very important. The first coil is the RF transmitter. So RF transmitter is the radio frequency transmitter, that is the short radio frequency pulse which is applied onto the sample. It is given with the RF transmitter, and then there is a coil which is the detector. So whatever you are having a resonance within the atom, it is collected by the detector. Now these days technology have become really advanced. What usually the mechanism is being done is the RF signal transmitter or RF transmitter actually becomes detector after transmitting the RF signal. So what happens, there is only one coil, it gives the RF pulse, and then that same coil also acts like a detector and eventually captures the signal. Okay, and this capturing of the signal is being translated in the form of a spectroscopy pattern. Right now we saw, or we have been taking of proton as an example, but yes, there were others also, and we have to also understand why we have to use them and how we can use them. So in natural abundance, as I was telling, protons are present almost like 99%. They are everywhere, so their natural abundance is very high, and that is why for most, or almost like for every NMR spectroscopy people, a proton is the first choice of interest, or it is the first choice because they are naturally abundant. It is easy to get signal out of them, and then you don't have to prepare your samples in a particular way, or you don't have to add any isotope to enrich the signal. You get enough signals, right? But there are others also like 2H, 3H, they are also active, but their natural abundances are very less. So when we are getting something automatically with a natural abundance of almost 100% and it is NMR active, why not go for it? And why? So deuterium, as I was saying, is used to as a substitute of water to dissolve your NMR sample or NMR compound which you want to study or elucidate, and then once you dissolve in D2O, it becomes in liquid format. You put it in the sample holder and then you can study. Okay, now other thing is like you have carbon, as I was telling, C12 is very predominantly available in the nature. It is the natural abundance is almost 99%, but the problem is it is the spin quantum number is 12, so that is odd. Is what we are looking for, but here spin quantum number 12, which is even, and even number is inactive in terms of NMR activity. So we have the other isotope which is C13, and although C13 is NMR active and everything, but its natural abundance is very poor, and that is where we have to either enrich C13 onto a sample at most of the times where you want to get C13. So after proton, carbon is the second choice, and then you have the nitrogen. Again, same story with nitrogen, N14, which is naturally very much abundant, but it is not no. So it is active, and at the same time N15, which is naturally not much abundant, but at the as you can see here, both N14 and N15 can be used. So when we are studying for different bones, when we are studying from minerals, so there we see if there are nitrogen presence or there, and based on that we use N14 or N15. There are a few more like oxygen, fluorine, you have chlorine, you have phosphorus. So phosphorus P31 is very commonly used, chlorine 35, oxygen again 17, 16 and 18 isotopes are inactive for NMR, and that is why we are not using it. So we have to keep this in mind how we are calculating it. As you can see here, in case of oxygen, 16, 18 both are even, and that is why they are inactive. Okay, so what are our like NMR active samples? What is the natural abundance? If they are NMR active, if their natural abundance is good, that is a win-win situation. If not, then we have to think of enriching our with the isotope. Now coming to the spectra part. So what we saw, we have positioned the sample, and then what we got, a plot. So this is what a standard or a very simple NMR spectra looks like. Okay, so NMR spectra, you see on the y-axis you have intensity, and on the x-axis you have ppm, or there is a chemical shift in terms of ppm. So what is ppm? ppm is parts per million. Okay, so this is this many parts, or the number, as you can see here, this part per million is being found here, and the depending on that, what is the intensity. So what indirectly we can say is, from ppm, parts per million, we can quantify the concentration. So we know what micromolar concentration we are using in our sample, and from that micromolar concentration we are making a dilution with a D2O or with any other NMR solvent which is available in the market, and we have to once we know this, we can plot the intensity of different protons once we're doing a proton NMR spectra, and then we can work out onto the concentration of each of these groups, and then find out the structure of it, and then cumulatively calculate the entire concentration of that particular structure. Okay, so this will give a very crucial and initial idea about what is the concentration you have used and what concentration is being detected, because the number of protons. So now if I talk of intensity, the intensity, suppose I have one proton, just example, I have one proton, my intensity will be less, because the signal coming out from one proton will be obviously less. And if I have suppose 3 protons at the same position resonating at the same frequency, I will also have a single peak, but my single peak intensity will increase onto the intensity or increase onto the height. So that will give me an idea that it is not the single proton which is resonating at the same position, but it is multiple protons which are resonating, and that gives me a clue to how many protons are there in that vicinity, which, or if it is a proton, so one proton maybe will be attached to the neighboring carbon, and with this say neighboring carbon there may be other protons, so it can be CH2, it can be CH, it can be CH3. So if it is CH3, then there are 3 protons which are resonating at the same environment, and that is why 3 protons cumulatively will give you a higher intensity peak. The height of the peak will be more. And if it is just a CH, that is only one proton, and that particular proton intensity or the resonance of that particular proton will be much lesser, although at the same position. So from there we can find out, okay, yes, so this particular proton is experiencing the magnetic field and they are resonating at this particular thing. And with this what we see is also increasing in the chemical shift. So I'll come to the chemical shift in a while, because there we have to go a little bit on the structural part, and from there how you are going to the electronegativity due to the electronic clouds which are floating around the particular nucleus. So in that particular proton, what is the shielding effect, what is the electron negativity it is experiencing, everything will have to be taken into care, and then only this movement or this positioning onto this chemical shift scale will be more precise. Now when we have a scale, we always need a reference, right? So reference in this case, we use usually TMS is tetramethylsilane. So you have a silane, and on this silane there are 4 methyl groups. So CH4, 4 CH groups will be positioned, and this tetramethylsilane will act as a you can say as a reference spectra. So what usually as NMR spectroscopist, when they get the spectra, they add this reference solvent along with the sample. So what happens is, this is resonating, this will be resonating very close to 0. I know this peak, and this peak will resonate very close to 0, because there are 4 methyl groups, and I know the pattern of the 4 methyl groups resonating at the same place. So I know this is the reference, and when I know the reference, I will have to set this particular peak at 0. Now why this is important? Because once you set your reference peak at 0, rest of the peak positioning will happen accordingly. Okay, so if I have to understand the ppm position of this particular proton, I will not be knowing this position, right? I will get a spectra, but I need a reference peak, and this reference peak position I know it very well, and which I will set it at 0. Once I set it at 0, I automatically will see that rest of the peaks will get positioned accordingly. Okay, and that is why it is very crucial not to forget to add your reference solvent. So whenever you are working with NMR, you will need to have a reference solvent, because based on that you are going to reference, you are using it as a reference peak to align and do the referencing for rest of the peaks. If your reference peak is wrong, rest of the peak positioning will definitely be wrong. And in NMR you cannot do or you cannot take a chances of a wrong referencing. Even the shift of 0.1 or 0.2 ppm can change the entire structure. That is why this referencing is very, very crucial. Okay, so this is something which I'm emphasizing, because that will be telling you that how precisely you have done it and how precisely you are going to get your results out of it. Now, these are some of the important informations which we'll be discussing in a few slides. The first is, yes, position of the signals. Now it indicates what type of the proton the molecule contains. So positioning of the signal. Now if I again see the positioning. So for positioning there are two factors, because the scale is a chemical shift scale. But if I talk of chemical shift, I need to explain to you what is chemical shift precisely, and what is shielding, what is electronegativity, okay, and why these parameters or these factors are important to be discussed, because they actually guide or influence the positioning, or influence the you can say the positioning of the peak in the chemical shift. Okay, so the first thing is, just get an idea, or just imagine there are two protons, okay, and respective atoms we come to, and these respective atoms, they are very closely positioned to one another. So we are studying two protons which are present in the respective atoms, and they are closely positioned. Now you have a nucleus, you have electron cloud around them revolving for both the atoms. Now what happens is, they are very close to each other. The electronic cloud, once revolving, will also be closer to the other electronic cloud of the other atom. Now this resultant, a negative charge, will create a repulsion. Okay, so this repulsion will create, because of the positive because of the same charges, the negative charges, and this repulsion will change their orientation. Now the thing is, these atoms in an overall structure, they are positioned in such a way, they are linked with other neighboring atoms in such a way that they cannot break free, they cannot move, but at the same time they are repelling with each other. So it is like two neighbors, they have bought an apartment, they are very near to each other, they are neighbors, right? But they don't have good, cordial relationship among them. They don't like each other's face, and at the same time they cannot leave their house and go and settle down somewhere else. So they have to, because they have purchased a flat, they have to stay there because they have invested heavily onto it. So they cannot move out. At the same time, they don't stand each other's face. So similar situation is happening with different atoms, and when this mutual dislike increases, the enmity between them increases. Similarly, when the charge or the electron cloud around these two atoms, if they are more, the charge will be more, and the electronic repulsion or the charge repulsion will also be more, very high, and the net repulsion will be much more, but they will be affecting your positioning, they will be affecting your chemical shift value. Okay, the other scenario is, I have atom and I have a dense electronic cloud revolving around that particular atom. So that atom has a dense electronic cloud and it is revolving around that nucleus, right? Now when I am talking of a dense electronic cloud revolving around onto the orbitals, what actually I am trying to tap is the proton which is present there, right? So the proton is of my interest because it will respond to the external magnetic field. Now, when it is responding to the external magnetic field, the magnetic field will also have to pass through that dense electronic cloud and then go to the nucleus. Resultant or the resultant frequency after getting that RF pulse will also have to be cached by the detector, and that will also experience some amount of electronic cloud because it is always present onto it, it is revolving onto it, right? So the point is that this electronic on a cloud revolving around the nucleus, it will give a shielding effect, it will create a shielding effect. So all of you, I think if you can correlate with the global warming, so you see from the sun you have the heat waves coming inside, and earth is suppose the nucleus here, right? So if there are no cloud, there is no carbon dioxide, there are no pollution in the environment, what happens is the heat can easily go out to the external atmosphere from the earth's surface. So that is the frequency which the signal or the radio frequency signal has been absorbed, and then from there, from higher energy state to lower energy state, this signal is being emitted out. We are going to tap that as an NMR signal. But what is happening, because of this shield of electron, it is like clouds, they are they are like pollution on the earth's atmosphere, they are not letting the entire signal from the earth. So like in earth you have the heat, and the heat is not able to escape on outside just because of this shielding effect, the greenhouse effect caused by this pollution. So similarly, the frequency or the release frequency or the signal, NMR signal, which you are trying to get from the proton will be shielded by the electronic cloud revolving around it, and the net resultant signal which is acquired will be much less. That is where your shielding effect will be very important. Now how shielding effect or why shielding effect, that I have told you, but how do you know what is shielding effect? But how do you know how much shielding effect is going to be high or less? It is directly the electronegativity factor. Okay, so if you see from the valence electrons, the more the valence electrons, the electronegativity of that particular atom will be more, and based on that more and more electronegative, there will be more electron floating around, and based on the more electron floating around or electron cloud floating around the nucleus, the shielding effect will be higher, and the resultant signal which will, so the induced field, you see decreases the strength of the magnetic field felt by the nucleus just because of this electron cloud. The external magnetic field, which is the B naught, which is the nucleus supposed to experience, it will be reduced, it will not be the same, as you can see here in both the diagrams. So this is because of the proton being surrounded with the electron density.